Welcome back to the video course on fluid mechanics. The last lecture we were discussing about the pipe flow systems. We have seen various aspects of laminar flow conditions and turbulent flow conditions with respect to the pipe flow, and also with respect to the various losses. Also with respect to pipe flow, we have discussed the major losses, minor losses. So, in today's lecture further we will discuss the various pipe losses. First we will discuss the various aspects of major pipe losses, and then we will discuss the minor pipe losses. So, as we discussed earlier, this in pipe flow with respect to the real fluid, we have the shear stress on the pipe wall, and then shear force is there, and then the viscosity plays a major role. So, all these aspects we have seen earlier. So, now one of the most important equations as far as major pipe loss is concerned, it is called the Darcy-Weisbach equation. So, first we will start with the Darcy-Weisbach equation, the derivation of Darcy-Weisbach equation. So, let us consider a pipe like this. A flow is in this direction, and the diameter of the pipe is d and radius is r, and it is at an angle theta, as the center line is at an angle theta as shown here. So, let us consider two sections between 1 and 2. Say at section 1 the height to the center line, the datum height is z1, and at section 2 the datum height is z2 from the center line. So, the section which we consider is delta L. So, for such a section, let us consider say the fundamental equations. So, first we will apply the Bernoulli's equation between section 1 and 2. So, here at section 1 the pressure is P1, and at section 2 pressure is P2, and the velocity at section 1 be V1 and velocity at section 2 be V2. So, and then due to the viscous effects and the shear stress effects, there is the friction loss. So, let it be represented as HF. So, by applying the Bernoulli's equations between section 1 and 2, we can write P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2 plus HF. So, this is obtained from the Bernoulli's equation. So, here HF is the loss with respect to the friction or with respect to the viscosity effect, so between section 1 and 2. So, now the HF is what we want to find out from here, this equation from the Bernoulli's equations. So, from the continuity equation we can write A1 V1 is equal to A2 V2. So, here now we consider the pipe flow. So, the diameter is same. So, A1 is equal to A2. So, between section 1 and 2 we can see that here V1 is equal to the average velocity at section 1, and section 2 V1 is equal to V2 from the continuity equation. So, after using the continuity equation in this equation number 1, we can write the head loss due to friction HF is equal to P1 by rho g minus P2 by rho g plus Z1 minus Z2, the difference in datum head. So, this we can write as, if say P1 minus P2 is the pressure loss, pressure difference. So, delta P by rho g. So, HF is equal to delta P by rho g plus delta Z, that means the datum head difference between section 1 and 2. So, as in equation number 2. Now, let us use the momentum theorem between say section 1 and 2. So, here say we have seen that the pressure difference between section 1 and 2 is delta P. So, by applying the momentum equation along the flow direction, so delta P into pi r square, where r is the radius of the pipe, plus rho g into pi r square into delta L sin phi. So, here the forces acting are the pressure force, then the weight of this fluid. So, that is obtained as rho g into pi r square into delta L sin phi, and then the shear force. So, tau w into 2 pi r into delta L. So, that should be equal to the change in momentum, so rho q into V2 minus V1. So, here since V1 is equal to V2, so this is equal to 0 as in equation number 3. So, where q is the discharge through the flow through the pipe, and then r is the radius of the pipe. So, here the net forces, the forces acting on this pipe element between section 1 and 2 are the pressure force, then the weight of the liquid between section 1 and 2, and then the shear force. So, the net force, the algebraic sum of the force should be equal to the rate of change of momentum. So, rate of change of momentum is rho q into V2 minus V1, where V2 is the velocity at section 2 and V1 is the velocity at section 1. So, now here we consider the flow as steady and fluid is incompressible. So, with respect to all these assumptions, we can see that here since velocity V1 is equal to V2. So, rate of change of momentum is 0. So, that the algebraic sum of the forces is equal to 0 as in equation number 3. So, now here with respect to this figure, this delta L is this length. So, now as Z1 minus Z2, that means delta Z we can write as delta Z is equal to delta L sin phi. So, after putting this delta Z is equal to delta L sin phi, so in this equation number, say here equation number 3. So, we get delta P into pi r square divided by rho g pi r square plus delta Z is equal to tau w into 2 pi r delta L divided by rho g pi r square, where tau w is the wall shear stress. So, now say this we can simplify as delta P, this equation we can simplify as delta P by rho g plus delta Z is equal to 2 tau w into delta L by rho g r. So, now if you put in this equation number 2 by considering this equation number 2 coming from the Bernoulli's equation. So, we get Hf, the head loss due to friction, Hf is equal to 2 tau w into delta L by rho g r, since delta P by rho g plus delta Z is also here. So, from the equation number 2 we get Hf is equal to 2 into tau w by into delta L by rho g r. So, now the wall shear stress tau w can be expressed in functional form. So, wall shear stress is a function of the density of the fluid, the average velocity, viscosity, dynamic coefficient of viscosity mu, the diameter and the roughness height. So, this tau w is a function of rho v, mu, d and k. So, k is the average roughness height and v is the average velocity. So, if you do a dimensional analysis using Buckingham's pi theorem, which we discussed earlier, we can write this, we can derive an expression for this tau w in terms of these parameters rho v, mu, d, k, or in terms of Reynolds number R e d and k by d. So, from the Buckingham's pi theorem we get 8 tau w by rho v square is equal to as a function of f, or a function of Reynolds number and k by d, where k is average roughness height and d is the diameter of the pipe, and this is equal to f, where f is the friction coefficient. So, this we can show this 8 tau w by rho v square is the friction coefficient as far as pipe flow is concerned. So, now this what we got from the Buckingham's pi theorem, we can put it back here with respect to tau w, and then we can get an expression for the head loss due to friction Hf we can obtain. So, now hence tau w is equal to f rho v square by 8. So, that can be written as f by 4 into half rho v square. So, we can write Hf is equal to 2 into tau w delta L by rho g r. So, that is equal to, after substituting for tau w, Hf is equal to 2f rho v square into delta L by 8 rho g into r. So, that is equal to 2f rho v square to delta L by 8 rho g d, where d is the diameter. So, d is 2 times, say this r is equal to d by 2. So, in terms of when we write this in terms of, it will be 2 into delta L by d. So, finally, we get the Hf as Hf is equal to f L v square by 2 g d. So, here delta L is replaced by, say, the length which we consider. So, here now we have derived the Darcy-Weisbach equation by considering the momentum principle and the Bernoulli's equation between section 1 and 2, and then this equation is applicable for most of the fluid flow for both laminar and turbulent conditions, and it is any kind of duct flow. It is not essential the flow, the pipe to be should be the circular in cross section. It can be any kind of pipe flow, and this Darcy-Weisbach equation is applicable to both laminar and turbulent conditions. So, this Darcy-Weisbach equation is one of the basic equation, one of the fundamental equation, and very much used equation as far as the head loss calculation with respect to the friction loss between two sections in any kind, in most of the pipeline problems or pipe flow systems. So, now the equation which we consider the Hazen-Williams flow as far as laminar flow condition which we considered earlier. For Hazen-Williams flow, we can write V is equal to delta P d square by 32 mu L, where delta P is the pressure difference and d is the diameter, mu is the coefficient of dynamic viscosity and L is the length. So, V is equal to delta P d square by 32 mu L, and head loss we can represent as HF is equal to P1 minus P2 by rho g. So, that is equal to delta P by rho g. So, that is equal to, by using this equation here, 32 mu VL by d square into rho g. So, that is equal to FL V square by 2 GD. Hence, say as far as laminar flow condition is concerned, we can show that F is equal to the friction factor, F is equal to 64 by Reynolds number Re, where Re is the Reynolds number, say rho Vd by mu as far as the pipe flow is concerned. So, finally, we get the coefficient of friction F is equal to 64 by Re Reynolds number by considering the Hazen-Williams flow as the case of laminar flow conditions. So, that way we can show that the Darcy-Weisbach equation which we have derived is valid for laminar flow as well as turbulent flow conditions. So, starting from for the earlier case when we considered the Bernoulli's equation and the momentum theorem, we got the Darcy-Weisbach equation. Similarly, by considering the Hazen-Williams flow also, we get the same expression HF is equal to FL V square by 2 GD. So, now let us discuss more detail about this Darcy-Weisbach equation and then the coefficient of friction, since in most of the pipe flow system, one of the most important aspects as far as flow is considered is the coefficient of friction. So, this HF is equal to FL V square by 2 GD. The head loss equation as far as given as Darcy-Weisbach equation is, say here you can see that the head loss is given in terms of the friction factor F. So, you can see that the head loss is directly proportional to the friction factor F and directly proportional to the length of the pipe and directly proportional to the square of the velocity, average velocity, and inversely proportional to the diameter d. So, with respect to this Darcy-Weisbach equation, we can calculate the head loss, which we can say for any kind of pipe flow systems, we can calculate the head loss by using the Darcy-Weisbach equation in terms of the friction factor F, in terms of the length and velocity square and with respect to the diameter of the pipe. So, this Darcy-Weisbach equation is considered to be the best empirical relationship for pipe flow resistance calculation. So, in most of the pipe flow system is considered, we have to calculate the head loss with respect to the friction. So, this equation, the Darcy-Weisbach equation, is one of the most commonly used equation as far as head loss is considered, and this equation is equivalent to the Hazen-Williams equation for laminar flow as we have shown in the last slide. So, only exception is that the empirical friction factor F is introduced here. So, with respect to this, here you can see this empirical friction factor is one of the important aspect as far as this Darcy-Weisbach equation is considered. So, we have to say for all the this F depends upon various parameters like material of the pipe and then flow conditions and then also say the pipe, the various other parameters with respect to whether the material of the pipe, etc. So, say we have to by considering the Darcy-Weisbach equation, we have to see the friction coefficient or friction factor as far as the considered pipe flow. So, now here with respect to the Darcy-Weisbach equation, so here HF, the head loss, the major loss is the energy or head loss expressed in length units due to the friction between the moving fluid and the duct. So, here what we consider here is say with respect to the pipe flow which we considered. So, when we consider any kind of pipe flow like this. So, here say between two sections. So, here the head loss between, say if d is the diameter of the pipe and L is the length between this. So, here by considering this you can see that the head loss between say section 11222. So, we can see that say here the friction factor is the most important parameter, and then we get the energy loss as due to the friction between the moving fluid and the duct in terms of as a length unit. So, the friction factor F is the most important parameter in the Darcy-Weisbach equation, and F is a complex function of the Reynolds number and relative roughness. So, various experiments conducted with respect to various pipe flow systems, it was shown that this friction factor F is dependent upon the relative roughness of the pipe, that means the pipe material, and it's whether it is smooth or rough. So, F is the friction factor depends upon the pipe material, its roughness, and also the Reynolds number, that means with respect to the flow condition. So, F is a function of Reynolds number and relative roughness, and the Reynolds number for pipe flow is rho V d by mu. So, now say depending upon the case whether the flow condition and also the pipe material, and then whether the pipe is smooth or rough, we have to find this friction factor. So, say for example, say now if we let us consider the various choices of F for smooth pipes. So, for laminar flow, that means when the Reynolds number is less than 2000, say we in the calculation we do not have to worry about the friction factor. So, pipe reference is not a factor. So, we can directly obtain the pipe reference, the friction factor we can directly calculate F is equal to 64 by Reynolds number, and for turbulent flow say up to this between 4000 to the into between the range of 10 to the power 5 to 4000 the Reynolds number range, Blasius calculated this friction factor is equal to 0.3164 divided by R e to the power 0.25. So, like this for various conditions based upon various experiments and some of the empirical relationships, say this friction factor has been calculated for various kinds of pipe flow, for various pipe material and reference factors. So, as far as laminar flow is concerned, we can directly get with respect to Reynolds number friction factor F is equal to 64 by R e, and then say as far as turbulent flow is considered, say Blasius has shown through experiments that F is equal to 0.3164 by R e to the Reynolds number to the power 0.25, but other ranges also various equations are available. We will be discussing in detail about this friction factor and various relationships available in literature. So, now here the choice of F for rough pipes. So, as I mentioned, there are empirical formulae and diagrams to determine the friction factor F depending upon their roughness and the Reynolds number. So, the commonly used say methodologies include the Moody's diagram, Swamee and Jain formula, and Nikuradse experiment results, and Colebrook equations. So, these are some of the commonly used methodologies to estimate this friction factor F. So, we will discuss each of these methodologies in detail as far as the friction factor for rough pipes are considered. So, first let us see the Moody's diagram. So, this Moody's diagram has been derived by conducting large number of experiments at various flow conditions, flow at various Reynolds number, and also flow through various diameter pipes and various smooth, rough, and say different kinds of roughness values. A large number of experiments were conducted, and this Moody's diagram has been derived. So, this Moody's diagram is used for rough pipe in turbulent flow condition. We use the Moody's diagram to obtain the friction factor F. So, this Moody's diagram is obtained through experimental data that relates the friction factor to Reynolds number, and then it is obtained for fully developed pipe flow over a wide range of wall roughness. So, the Moody's diagram gives the say from the Moody's diagram, depending upon the Reynolds number, what kind of say the turbulent, say it is whether it is transitional turbulent, different ranges of turbulent flow, we can obtain the friction factor with respect to the wall roughness. Friction factor is we can directly obtain to do the other calculation. And then say the turbulent portion of the Moody chart we can represent by the Colebrook formula given as 1 by root f is equal to minus 2 log 10 E by D divided by 3.7 plus 2.51 Re root f, where f is the friction factor, Re is the Reynolds number, E is the roughness height, and D is the diameter of pipe. So, this turbulent portion of the Moody's chart, so experimentally shown these values, and also it can be verified that these values in the Moody's chart is very similar to the Colebrook formula given by this equation. So, here this slide shows the Moody's diagram. So, here on the x axis the Reynolds number is represented, and on this axis the friction factor is given, and here the curves are given for various E by D ratio, where E is the roughness height, the relative roughness E by D, D is the diameter, E by D is equal to 0.03, like that for various values, and the roughness for various roughness or E by D ratios, and the Reynolds number, the friction factor is given here. So, there is smooth pipe range. So, whenever it is almost the E is almost 0, that means smooth pipe. So, here E by D ratio is 0. So, that is this is the lowermost curve, and then we can see that depending upon the Reynolds number, say we can obtain the friction factor with respect to say various ratios of E by D. We can obtain this curve or this line is for laminar flow, and this range is for the transition. So, actually you can see that the Moody's diagram is commonly used to find out the friction factor for turbulent flow region. That is where we use this F factor, friction factor commonly. So, it is given for various curves are given for various E by D ratio as shown in this slide. And then, so as I mentioned, various methodologies are available. So, first one which we discussed is the Moody's diagram, and then large number of other relationships say to obtain the friction factor are available in literature. So, few of these relationships we will discuss here. So, Swamee and Jain formula. Next one is the Swamee and Jain formula. So, these are some of the empirical relationship derived by this Swamee and Jain based upon a large number of experiments. So, here Swamee and Jain they have shown that F is equal to the friction factor F is equal to 1.325 natural log 0.27 into E by D plus 5.74 into 1 by Re to the power 0.9 all to the power minus 2 as shown in this equation, and this is valued, the friction factor, this is valued in the range of E by D ratio of 10 to the power minus 6 to 0.01, and the Reynolds number range of 5000 to 3 into 10 to the power 8. So, for this range, this equation for friction factor is valid as derived by Swamee and Jain, and then head loss directly we can obtain HL is equal to 1.07 into q square L divided by G into d to the power 5 natural log E by 3.70 plus 4.62 into nu d by q to the power 0.9 all to the power minus 2, where q is the discharge through the pipe, and d is the diameter, and nu is the coefficient of kinematic viscosity, and E is the roughness height of the pipe material, and L is the length which we consider. So, this equation gives the head loss. So, here this is the same range with respect, it is obtained with respect to this F factor here. So, this equation is valued in the range of E by D ratio of 10 to the power minus 6 to 0.01, and the Reynolds number range of 5000 to 3 into 10 to the power 8. And then we can also Swamee and Jain derived the equation for discharge. So, discharge Q is equal to minus 0.965 G into d to the power 5 HL divided by L to the power 0.5 natural log E by 3.7 D plus 3.17 nu square into L divided by GD cube into HL all to the power 0.5. So, this equation for the discharge is valued for Reynolds number greater than 2000 as given by Swamee and Jain, and here is the roughness height and nu is the kinematic viscosity. And then they also got say to design a pipe. So, they derived so you can see that while designing the pipe for the given discharge, it depends upon various parameters. So, some of the equations which Swamee and Jain derived based upon this equation, they got an expression directly, they derived an expression for diameter for the pipe. So, D is equal to 0.66 d to the power 1.25 L q square by G H L to the power 4.75 plus nu q to the power 9.4 L by G H L to the power 5.2 to the power 0.04. So, here H L represents the head loss, this H L represents the head loss. So, like this, so as I mentioned, this relationships were derived based upon a large number of experiments, and then using some of the available empirical relationships, already available relationships. Various scientists and engineers derived a number of equations as far as the friction factor, head loss, and also discharge, or to design a pipe to find out the diameter of the pipe. Various relationships are derived. So, these equations shows the relationship as far as friction factor, head loss, discharge and diameter of the pipe is concerned, derived by Swamee and Jain. And then say in literature, say some of the other important relationships are given by Nikuradse through his experiments. So, he also produced some charts for the say with respect to the head loss and with respect to the friction factor by relating to the Reynolds number. So, Nikuradse conducted a large number of experiments for rough and smooth pipes, a number of different kinds of pipes and different materials, and he has shown that for a rough pipe, the mean height of the roughness is greater than the thickness of the laminar sublayer. So, Nikuradse through his experiment showed that for rough pipe, the mean height of the roughness is greater than the thickness of the laminar sublayer, and Nikuradse conducted all these experiments by artificially roughening the pipe by coating them with the sand. So, in the laboratory he produced a number of sections of the different kinds of pipes by sand coating, artificially roughening the pipe by sand coating, and then he produced graphs for F versus Reynolds number, for F against the friction factor against the Reynolds number, for a range of relative roughness 1 by 32, 1 by 1014. So, various ranges of relative roughness, Nikuradse produced the graphs for F versus, that means the friction factor versus the Reynolds number, starting from 1 by 30 relative roughness 1 by 32, 1 by 1014. So, this graph shows the regions of for various flows. So, here this is the graph derived by Nikuradse with respect to large number of experiments he carried out in the laboratory. So, here this is very similar to the Moody's diagram which we have seen earlier. So, here friction factor on log scale is put on this is on log scale on the y axis, and Reynolds number on log scale is given on the x axis, and then relative roughness is given here like epsilon by d and or E by d. E is the relative roughness height. So, 1 by 30, 1 by 60 like that. For various relative roughness, Nikuradse produced this graph, and here this is for rough turbulent zone, and here this region is for transitional turbulent zone, and here this is the smooth turbulence, smooth for smooth pipe, and this is the laminar range. So, after conducting say large number of experiments with respect to various flow conditions, with respect to various pipe material, with respect to various roughness height, Nikuradse produced this graph, and that gives. So, from this graph also we can obtain the friction factor for various Reynolds number and also various relative roughness. So, like this. So, this is say first we discuss the Moody's diagram, then we have seen the Swamee-Jain formula, and Now, the third one is the Nikuradse plot, and the next one is the Colebrook's equation. So, Colebrook derived some of the relationship with respect to the friction factor and Reynolds number. So, here Colebrook showed that for smooth pipe flow 1 by root of is equal to 0.86 natural log Re root of minus 0.8. So, this is for smooth pipe flow, and in transition zone, that means between the smooth to rough, that transition zone, Colebrook showed that 1 by root of is equal to minus 0.86 natural log E by 3.7 d plus 2.51 divided by Re to the power root of, where Re is the Reynolds number and F is the friction factor, D is the diameter, E is the height of roughness height. And then for completely turbulent zone, this can be reduced to this condition for fully turbulent and rough zone. So, here this is 1 by root of is equal to minus 0.86 natural log E by 3.7 d. This can be approximated from this equation. So, these equations are called Colebrook equations for friction factor for smooth transition or completely rough type flow. So, as we have seen, the Moody's diagram is very similar to what is given in the Moody's diagram is very similar to what is given by Colebrook equation. So, Colebrook equation is also one of the most accurate kind of equation as far as friction factor is considered. And another kind of equation, say, is called Hazen-Williams formula for friction factor F. So, this is given as F is equal to 1059 divided by C to the power 1.85, D to the power 0.02, Re to the power 0.15, where C is the Hazen-Williams coefficient. We will be discussing about this coefficient later, and D is the diameter, Re is the Reynolds number. So, diameter should be in millimeter here. So, this F is given by the friction factor is given like this by Hazen-Williams formula. And then another important formula used in literature is called the Barr formula. So, here the Barr formula for friction factor is given as 1 by root of, that is equal to minus 4 log 10 E divided by 3.71 d plus 5.1286 divided by Re to the power 0.89. So, here also this is the relationship between the friction factor and relative roughness and the Reynolds number. So, like this there are few more formulae or relationship available for friction factor in turbulent flow condition. This most of the equations relates friction factor with respect to the relative roughness and the Reynolds number, as we have seen the Colebrook equation or Barr's equation, and also as shown by Nikuradse. So, out of the charts and equations and the Moody diagram and the Nikuradse charts, we can see that this Moody's diagram is one of the most accurate in determining the friction factor. So, also we can see that say the approximations given by Colebrook and Barr's equations are very close to the what is given in Moody's diagram. So, in most of the pipe design and analysis, we can use this Moody's diagram to get the friction factor with respect to the Reynolds number and the relative roughness, since this Moody's diagram is found to be one of the most accurate relationship or the chart available, or it is very similar to the results are very similar to what we get from the Colebrook equations or the Barr's equation. So, in most of the pipe design is considered, either we can use the Moody's diagram or we can use the Colebrook's equation. So, now we have seen that this in this when we discussed about the major losses as far as pipe friction is considered. So, say one of the important factor is the roughness height of the pipe with say as in the inside the pipe wall. So, you can see that with respect to various materials. So, we have seen that with respect to various material, this roughness height is changing. So, with respect to nature of interior surface and equivalent roughness in terms of is given here for various materials. So, typical roughness values are given, say for example, copper, lead, brass, glass, plastic. So, the pipes made up of this material and the roughness height varies from 0.001 to 0.0025 and then if the pipe is made up of riveted steel, it goes from large value like 0.9 to 9 and steel commercial pipes, this roughness equivalent roughness varies from 0.045 to 0.09. cast iron pipes are considered, then we can see that the equivalent roughness height varies from 0.25 to 0.8 millimeter, and concrete pipes depending upon the finishes. So, you can see that concrete or wood is considered the roughness height, or the whether the pipe is smooth or pipe is the rough depending upon the finishes given to the material. So, here for concrete pipe this equivalent roughness varies from 0.3 to 3 millimeter, and wood stave is considered this varies from 0.18 to 0.9 like that. So, for different material depending upon the material considered and the finishes given, and we can see that the roughness height changes. So, equivalent roughness height changes, and accordingly we can see that the friction factor also changes as given in the various relationships, various methodologies which we discussed like Moody's diagram or Colebrook equation. So, depending upon the relative roughness, the friction factor changes, and according to as the friction factor changes, the head loss also changes. So, all these important aspects we have to consider in the design of pipe flow systems, design of the pipes while considering the considered typical system. And now also you can see that one of the most commonly used equation for the pipe design is other than the Colebrook equation, which is obtained with the friction factors obtained by Colebrook. Other than this, one of the commonly used equation is Hazen-Williams equation. So, Hazen-Williams, the equation for velocity is given as V is equal to K into C into R s to the power 0.63 S to the power 0.54. So, here this equation is valid for water at temperatures typical of city water supply system ranging from 4 to 25 degrees centigrade. So, here S is equal to Hf by L, which is with respect to the head loss Hf by L, and Q is the discharge is given as V area into velocity. So, Q is V into A, and RH is the say is equal to D by 4, that is with respect to the A by P, that means the hydraulic radius is obtained as RH is equal to D by 4 for circular pipe, and K is a unit conversion factor as far as Hazen-Williams formula is considered. So, in the FPS system K is equal to 1.318, and in SI system it is 0.85, and RH is the hydraulic radius as discussed. So, Hazen-Williams equation is one of the commonly used equation as far as pipe flow design is considered, other than the Darcy-Weisbach and Colebrook equation which we discussed in detail, but Darcy-Weisbach equation is much more accurate than this Hazen-Williams equation. So, Hazen-Williams method is one of the popular methodology for pipe design among civil engineers, because its friction coefficient, this C here, this coefficient C is not a function of velocity or duct diameter. So, in literature we can see that various values for C are given. So, and Hazen-Williams equation is similar than the Darcy-Weisbach equation for calculating the flow rate, velocity or diameter depending upon which parameter we are calculating, for which we are designing. So, Darcy-Weisbach equation is one of the most commonly used equation. Other than that, Hazen-Williams equation is also used in the pipe design. So, this Hazen-Williams friction factor which we discussed, so for it depends upon the material. You can see in literature various values are given for C. So, like asbestos cement C is equal to 140, cast iron 130, whether it is new old say 20 years or 40 years old, this C changes like this. Concrete or concrete lined steel pipe system, it will be about 140, or if it is lined in wooden forms it will be 120, or say copper pipe, copper material is concerned 130 to 140. So, like this we can see this factor C as far as Hazen-Williams equation is considered. So, now so far we have discussed the major losses in a pipe system is considered. So, it is mainly to friction loss, HF or HL, what we consider the head loss or the friction with respect to head loss due to the friction. So, one of the most commonly used equation is the Darcy-Weisbach equation, which we have discussed. Only thing is that in Darcy-Weisbach equation we have to find out the friction factor, and other commonly used equation is the Hazen-Williams equation for the pipe design. So, for pipe design is considered, we can use either Darcy-Weisbach equation or Hazen-Williams equation, or some of the other methodologies, other equations available in literature. So, that is as far as the major laws is considered what we discussed so far. So, now we will discuss in detail about the minor losses in pipe flow. So, we have seen earlier that pipe flow losses are considered. There are major loss due to the friction loss, and there are minor losses due to say various conditions like expansion, contraction, or due to various pipe fittings like bends, then T junction, or say various connections, there will be minor losses. So, now we will discuss in detail about the minor losses in pipe flow. So, as we discussed in the last lecture, the minor losses occurs due to the presence of valves, elbows, joints, or contraction, expansion, etc. in the pipeline. So, generally a minor loss is expressed in terms of a loss coefficient k as a function of the velocity. So, we have seen this major loss already. So, like that in the minor loss also we represent the minor loss in terms of the velocity as a function of velocity multiplied by a coefficient k. So, generally HL, the head loss for minor loss is concerned, HL is equal to k into v square by 2g, where v is the average velocity, k is the coefficient for minor loss, g is the acceleration due to gravity. So, where k is determined experimentally for various fittings and geometry changes of interest in piping system. So, as we discussed earlier, depending upon the problem, there will be different kinds of say joints or different kinds of contraction, expansion, or junction, etc. So, depending upon the conditions, say for various, depending upon the material which we use for pipe construction, we will be having the values of this k. So, either we can determine through experiments, or sometimes depending upon the conditions of manufacturing, manufacturer may give the values also. So, now here we will discuss various aspects of this minor loss with respect to this equation, HL is equal to k into v square by 2g. So, as we discussed, the minor losses in pipelines are concerned, minor losses can be due to sudden expansion, sudden contraction, gradual expansion, entry loss, exit loss, and also losses due to pipe components like losses due to valves, bends, T, elbow, etc. So, as we have seen, say for example, if you are connecting here, there is a tank here, and now if you are connecting, putting a pipeline like this with various branches and then various joints, you can see. Now, say in such a system, say we may be distributing, say either for water supply, or say maybe for say various other kinds of network. You can see that we may be continuing the flow like this. So, in such a system, in the pipe network like this, we can see that say here maybe we may be connecting to another tank. So, and here this flow may be continuing. So, you can see here various connections, and say here if this is the say tank or reservoir. So, from here the flow takes place. So, in such a system you can see that there can be, say when the water enter from the tank to the pipe. So, there is an entry loss. So, here there is, you can see that there is an entry loss, and then here you can see that we provide here a bench. So, there can be loss due to bench, and then here you can see that there is a junction here. So, here, so there is a, we may give a junction. So, junction losses, and then there we may provide an elbow here, or there can be, depending upon the pipe diameter changes, there can be expansion. So, here also we can have expansion, or here we can have contraction. So, like that, and then say now finally when the this pipe joins here this tank, then you can see that again expansion. So, and here if you provide, there is a valve and then the flow continue here. So, this is a valve. So, like this here there is again a junction. So, there are number of components, you can see that in such a flow system there are number of components included, including the expansion, contraction, etc., exit, then entry loss, exit loss. So, we have to consider all these losses as far as pipe flow is considered. So, now we will discuss in detail. So, first let us consider the loss due to the sudden expansion. So, let us consider the figure below. Here you can see that a pipe is going, say here there is a pipe with a small diameter and then it is connected to a pipe with a large diameter. So, you can see that there will be a sudden expansion like this. So, flow is coming like this and then expands. So, here let us consider two sections here, section 1 and section 2. At section 1 area of cross section is A1 and velocity, average velocity is V1 and pressure be P1, and at section 2 area of cross section is A2 and velocity is V2 and pressure is P2. So, now this, let us consider the flow to be steady and the fluid is incompressible and turbulent flow and velocity is uniform. So, with respect to these assumptions, if you assume the shear force on pipe wall of short length between 1 and 2 is negligible and the mean pressure P dash of the eddying fluid in the expansion is almost equal to the pressure P1. So, from Newton's equation motion we can write P1 into A1 minus P2 into A2 plus P dash into A2 minus A1 is equal to P1 minus P2 into A2 as in equation number 1a. So, this we can simplify as, so this is simplify P1 A1 minus P2 A2 plus P dash A2 minus A1 equal to P1 minus P2 into A2. So, here we assume that P dash is equal to P1. So, that is why we got P1 minus P2 into A2 this equation, and then this is with respect to the change of momentum. So, we can write rho V2, this is equal to rho V2 into A2 V2 plus rho V1 into minus rho V1 A1 V1. So, this is the momentum. So, finally, we get, if we use the continuity equation, we can obtain P1 minus P2 is equal to rho into V2 into V2 minus V1 as in equation number 1b. So, here we consider the flow like this and here one section and another section is here. So, with respect to this equation, Newton's equation motion, we got P1 minus P2 is equal to rho V2 into V2 minus V1. So, now the energy equation, if we apply the energy equation to between section 1 and 2, we get V1 square by 2g plus P1 by gamma is equal to V2 square by 2g plus P2 by gamma plus HL, and where HL is the head loss. So, here between this section to this section, if HL is the head loss, we get V1 square by 2g plus P1 by gamma is equal to V2 square by 2g plus P2 by gamma plus HL. So, now say solving for P1 minus P2 by gamma from this equation, and if we use this equation 1a and 1b, we can write V2 square minus V1 V2 by g is equal to V2 square minus V1 square by 2g plus HL, we obtain from equation using equation 1a, 1b and equation number 2. So, finally, we get the head loss HL is equal to V1 minus V2 all square by 2g. So, that can be represented as V1 square by 2g into 1 minus A1 by A2 all square. So, here this loss coefficient here, this term, this, since we have already seen this head loss is represented as k into V square by 2g. So, if we consider this V1 square by 2g as a function, so we obtain here this loss coefficient k is equal to 1 minus A1 by A2 all square. So, here it is obvious that head loss varies as the square of the velocity, and it is true for all minor losses. So, here if A2 is extremely large, like a pipe opens to a reservoir, you can see that this A1 by A2, if A2 is very large, then it will be 0, then we obtain k is equal to 1. So, like that we can find out for various cases of expansion. So, with respect to this, k is equal to 1 minus A1 by A2 all square. So, where A1 is the cross section here at this section, the smaller section, and here the expanded section, the cross section is A2. So, if A2 is extremely large, as we have seen, the complete kinetic energy of flow is dissipated, as here say when the flow is going from here, this pipe flow is released to a tank or a reservoir. So, you can see that it is a complete expansion. So, the total kinetic energy of the flow is dissipated here. So, it is complete expansion. So, this is the expression for the expansion. So, similarly, if you consider the contraction, loss due to sudden contraction. So, let us consider the following figure. So, here this section 1, here this is the larger diameter and smaller diameter. So, here the velocity is V1 at section 1 and here the velocity at section 2 is V2, and then you can see that in the case of contraction there will be, say, a jet is formed, and then you can see that here a smaller section will be there which is called vena contracta. So, for loss due to contraction we can write Hc is equal to V0 minus V2 all square by 2g, where V0 is the velocity at this vena contracta and V2 is the velocity here at this junction. So, we can show that Hc is equal to head loss due to contraction is equal to V0 minus V2 all square by 2g. So, from continuity equation we can write V0, the velocity here, into Cc, the coefficient of contraction, into A2 is equal to V2 A2. So, Cc is the coefficient of contraction and V0 is the velocity at section here at vena contracta. So, the head loss due to contraction is obtained as Hc is equal to V0 minus V2 all square by 2g. So, with respect to this vena contracta, it is the section of the greatest contraction of the jet. Here you can see that the jet, say here, and the greatest contraction, and hence the head loss can be written as Hc is equal to 1 by Cc minus 1 all square into V2 square by 2g. So, with respect to this approximation here, the head loss with respect to the, we can write in terms of the coefficient of contraction, Hc is equal to 1 by Cc, where Cc is the coefficient of contraction. So, Hc is equal to 1 by Cc minus 1 all square into V2 square by 2g. So, here you can see that the expression is in terms of this velocity V2 here. So, Weisbach has calculated with respect to various ratios of A2 by A1, he has calculated this coefficient of contraction. So, that is given in literature. Here you can see for 0.1 Cc is A2 by A1 is 0.1, 0.624, like that various values have been calculated through experiments by Weisbach. So, now in the next lecture we will be discussing more about the, say, various losses, and then we will discuss the various aspects of the pipe flow design and then pipe flow systems for various conditions.